Hi, thanks for watching today. Today we'll be talking about effective practice methods. Not what goes on inside the practice room, but what goes on inside of our head, or how your brain reacts to your practicing. I'm Jeff Barbee, a doctoral student in Euphonium performance at the University of Missouri, Kansas City, as well as a recent graduate in the Master's of Arts in Higher Education Administration. Here is a short list of what we'll be talking about today. Short and long-term memory, synapses, the pre- and post-synaptic cleft, myelin, synaptic pruning, consolidation, as well as priming, the rest period, and brain plasticity. So you may ask yourself, why should we talk about this? Well, studies have shown students who understand what goes on during the learning process do a better job of retaining the information they were trying to learn. So I figured, why not learn more about the learning process and perhaps reap better results in our practice. The first aspect is short-term memory. Short-term memory is also called our working memory, and it deals with the information right now, such as your conscious decision to watch this video. It also deals with needing a phone number or a locker combination. After we use it, we pretty much lose it. If we use something enough, eventually it becomes part of our long-term memory. And our long-term memory is divided into two different types of long-term memory. Our first is our declarative memory, or memory I like to say that we declare that we were at, and this involves specific events or information that we really do not remember when we first learned. Examples of this would be a wedding day. Hopefully you declared that you were there to get married that day, or a car accident. The other example is your name, learning your ABCs or 1, 2, 3s. This information is stored in the hippocampus, which when needed is recalled upon. The other type of a long-term memory is our non-declarative memory, also known as procedural memory, and this deals with basic, what I consider motor functions, such as driving your car, driving to work, hopefully our scales. So how do these two work together? Well, think about your daily drive to work or school. You get in your car and you really don't think about what you do. Either the gas pedal means go, or what street to turn on, or where to park. Think about the last time you were at an ITEA conference, or any conference in particular, nothing in particular. You woke up from the hotel and you had to drive somewhere. Your procedural memory was you driving the car, knowing that the gas pedal meant go, seeing the stop sign meant stop. Your non-declarative memory was consciously thinking about where to turn or where to park. If you were to make this drive over and over again, eventually the non-declarative aspects of this process become procedural or non-declarative, and you really don't need to think about this drive. So this goes with building off learning new skills. You're really not starting from scratch. You're starting off from a base that you've acquired over time. So you might be thinking about a new skill, but you're subconsciously recalling on skills that you've known prior to help with this new skill. So a good example of this is learning a B-flat scale. You take the information that you learned from the scale and maybe apply it to a new etude in the key of B-flat. Then the next step would be to learn a solo in B-flat. So when you're focusing on the solo, you're not starting from scratch. You're using the skills that you had built up over time from the etude and from the scale. So a new piece, your declarative is focusing on the phrases and the melody of a new piece, while your non-declarative is looking at a half note or an eighth note rhythm and not really thinking about what that means, but just doing it. I used to believe that information in our brain was stored like a Word document on the computer, and this is far from the truth. The different aspects of experiences are actually broken down and stored in the appropriate places in the brain. These places are called cortices, and here is a picture of the different cortices located in our brain. We have our motor and our sensory cortex at the top. In the back, we have our visual cortex, as well as this area called the cerebellum. And our auditory cortex is in the middle. And this up here is our prefrontal cortex. Here's a list of what these cortices do. The visual deals with what we see, motor deals with how we move, the sensory cortex deals with what we feel, the auditory deals with what we hear, the prefrontal cortex is a little more complicated. That sets our expectations and our satisfactions. And the cerebellum in the back is considered by some a little brain on its own that deals mostly with motor functions. So once again, here's the picture, just to refresh your memory of where these are located. A fun fact, the Broca's area on the left side deals mostly with language. If you grew up in a bilingual household or picked up a language before the age of 7, the single area controls both of those languages. If you're like myself and trying to pick up a second language later in life, your brain will actually adapt and make a second Broca area to handle the needed skills for that language. In the motor and sensory cortex, there's a large portion called the homunculus. And the homunculus controls the nerve feelings in the different parts of our body. Here's a picture of the homunculus that kind of represents what or how many nerves are sent from each body part. If you were to squeeze your elbow really hard, you can feel or not feel any pain. Now, if you were to take the same pressure and squeeze your lower lip, you would notice that it hurts a lot more. And that's because if we look up top here, where our elbow has very little area on the homunculus, meaning that there's not a lot of nerves or cells going there. But if we look over here where our face is, we can see that there's a lot more nerves, hence why the pain is much more noticeable in our lip than in our elbow. The cerebellum in the back, as I said earlier, controls simple motor functions. This is very possible if you do the same warm-up day in and day out. The cerebellum could kick in without you really thinking about it. Perhaps that drive to school every day is where your cerebellum kicks in. You're not consciously thinking about it. It's also believed over time that this area of the brain has developed the ability to trigger emotions and certain things we hear. As we look at the cortices, they're each made of 6 layers. We've heard the terms gray matter and white matter. The outer area is gray matter, and what goes on in these areas is that the cortex communicates with just itself. It's in-house communication. As we dig deeper into the layers, we find more white matter, which is where communication between the cortices take place. Underneath our cortex, we have aspects of the brain that make up the central nervous system. We have our corpus callosum, which connects the 2 hemispheres. If we didn't have it, we would actually have 2 brains that would kind of function on their own. We also have our amygdala, which is an emotional storage center, also what I like to call our fear broker. If you were in a situation such as walking down a dark alley at night, your amygdala would kick in and say, this is the time to be fearful. It's also believed that it controls emotions as well. If you were to hear a wedding song or a school fight song when you're visiting your campus during homecoming. Also, we have the hippocampus, which, as stated earlier, our long-term memory is stored. This serves as our memory broker. If we use short-term memory enough, the hippocampus will say, hey, this information is important. We need to store it for the long term. Here is a picture of a neuron. Over here, we have our dendrites, which is where neurotransmitters enter into the cell. Here we have our cell body. Right here before what's known as the axon, we have our axon helic. And when neurotransmitters meet a certain threshold, they are then sent down through this axon, out through the axon terminals to another neuron. What is right here, it looks like little sausages. This is called myelin. And that kind of helps send the information even quicker through the cell. So myelin serves, well, I like to consider a speed insulator. the more you practice a certain repetition, the more this myelin builds up over the axon of a cell. If you practice correctly, hopefully, this is why you're able to play scales faster over time. If you were practicing something incorrectly, this is why it's very hard to break the habit, because myelin has built up over time, reinforcing the speed of this incorrect habit. Myelin becomes harder to regenerate after the age of 50, and if there's a skill set that you've built up over time and you fail to use it, it begins to break down and go away. The synapse. This is where neurotransmitters are sent from one neuron to the next. The axon terminals from one will send over the dendrite over the synaptic cleft, where the dendrite of the next cell will accept them. As we can see right here, it looks like the axon terminals are actually connecting with the dendrites, but there's actually that gap, the synaptic gap. And this is where that either neurotransmitters will be accepted or they won't be allowed in to be sent through the cell body for the sending process to be effective. So in our cells are depolarized until they accept neurotransmitters. And if they accept the neurotransmitters and it meets a certain threshold, a process called action potential, which is quite fascinating, either the cell will become depolarized, meaning that it will fire in a positive manner, or it will become hyperpolarized, which means that it will inhibit the cell even further. If neurons are sent over the synaptic cleft enough into the dendrites, eventually the dendrites will sprout what's known as dendrite spines. And what these are is to help receive the neurotransmitters. They also connect to other nearby cells and helps them fire through electrical action potential. The chemical is a slower process, but if it happens enough where the dendrite spines are able to sprout and connect with nearby cells, the electrical process can kick in and hence speed up the reaction. Brain plasticity is what happens when this process happens enough, is your brain will actually change and reform to recall this information at a much quicker rate. Synaptic pruning is important. This is what happens when unused neural pathways, they just die away. As you're learning a new etude or a new solo, at the beginning you might play incorrect notes, incorrect rhythms, which I kind of think of as like a plant with a bunch of different leaves and stems. But as you practice over and over the correct way, these extra pathways will go away, and you're just using the correct path to play the correct notes and rhythms. A process known as consolidation happens in our sleep. And what happens is that the day's functions or information that you've used travels through the cortex down to the hippocampus and back. This process takes between 5 and 6 hours. If you don't get at least 5 hours, like maybe perhaps a lot of college students, the day's practice is almost as if it didn't happen, because your brain's unable to retrace those steps and strengthen them. Here's an exercise dealt with a student. The student was going to play a one-handed piano exercise, but throughout time only going to practice with one hand. And up here was before the exercise, the area that controls each hand is pretty similar. But after day 3, 20 minutes after the exercise was practiced, we see a lot more activity. And this is because the brain is saying, hey, this information has been recalled on for 3 days. This is kind of important. And after 5 days, there's even a bigger difference. We also see a little more activity in the non-practiced hand because of the use of recalling for this exercise. Down here, we're measuring the brain activity through weeks. Week 1, there's little activity because this is still a new skill. The brain doesn't know if this is going to be important enough to recall upon. And as we go through, the pre-exercise area of the brain is more active, and the post-exercise isn't as active because the brain has actually changed to adapt to recall the skill. So, practice habits. Many of us practice in what I call mass practice, where you focus on one aspect for a long amount of time. This isn't bad if you can focus on this area, but what happens is that students will practice the same thing over and over for about an hour or so, and maybe only get about 20 minutes worth of good practice out of it. Another aspect is called random practice, where every 10 to 15 minutes you're changing the focus of your practice. Maybe you're shifting solos, or maybe you're looking at a different aspect in the solo, two different styles. This allows you to stay refreshed and focused on the task at hand. As far as sports, baseball players who practice in batting cages with random pitches, such as fastballs, curveballs, and random order, did better than batters who practice pitches in blocks, such as 15 fastballs, 15 curveballs. I think it's more of a realistic expectation of when they actually went to play in a real game that they're not going to get 5 fastballs in a row. It's going to be a mix. The pitcher's going to mix the pitches up to strike them out. The same can be said with basketball players. Those who varied their jump shots from different lengths had a better shooting percentage than basketball players who block practice their shooting. After you have practiced for an hour or so, it's good to go for a walk. And what happens here is that the brain is able to replenish the neurotransmitters that are needed to make positive changes for what you just practiced. So, the good aspects of good practice is focus. If you go to a practice session and you're not focused, do something else. Take a nap, go for a walk. Without the good focus, what you're going to work on is just not going to stick, and it's just not worth your time. Practice correct repetitions, even if it's a half tempo. What happens is that with the slow repetitions, you're going through the correct neural pathway, strengthening them. If you practice something up the tempo where you're not ready, you're not only maybe reinforcing the correct pathways, but you're also reinforcing the incorrect pathways, meaning that the synapse routes that we need to go away to help us play correctly are still around, and you're still encouraging them to grow and build that myelin. And most important, while you practice, stay positive. Don't get down on yourself. There are certain neurotransmitters that happen when you get stressed or depressed, and these actually inhibit the learning process. More ideas for good practice is breaking things down. Maybe focus on rhythm, then go back and focus on pitches. Singing and buzzing and modeling are great aspects. Modeling is taking the piece and just mentally going through it. Actually, close your eyes right now and think of a difficult lick in a solo or etude that you're working on. This is actually good practice because you're stimulating the brain to travel through the good neurons without the stress. In sports psychologists do this a lot with their athletes because there's only so many reps you can do before you're physically exhausted. So using modeling is another way to get in extra reps. To model, you have to buy into it and actually go through with the process and just not pretend to do it. It's an all-in or none kind of thing. At a music camp in Meadowmount, New York, they're famous for being able to teach students large amounts of rep in a short amount of time. And how they do this is that they re-focus students to practice the music in small chunks, small enough to where if an instructor were to walk by and hearing a student practice, they could not identify what piece they're practicing. And if a student does practice a piece in a large enough chunk that it is recognizable, the student gets in trouble. What happens, I don't know. They probably get a good talking to. But it's a very interesting aspect. The game of futsal, it's incredibly popular in South America and Europe right now. And it's like the game of soccer, except it's played on a gym floor with about half the people of a soccer team, and the ball is much smaller and harder to dribble. And what futsal does is that it focuses players to use the skills needed for the game of soccer in a much more intense environment. I feel this would be a good translation for tuba quartets or tuba band. In large ensemble music, it's widely known that the tuba euphonium parts do not have a lot of technical demands, especially in the lower levels. So being able to play in tuba ensembles or tuba quartets, players are able to handle more of that technical aspect that's just not there in large ensemble music. I think quartets and these kind of ensembles are very important for grade school and high school bands. They'll help develop the skills of these players much quicker than relying on band music. If you do have a bad habit or you've learned something incorrectly, do not focus or try to focus on correcting the habit. Instead, focus on learning a new habit, doing it slowly over and over and over. Focusing on breaking a bad habit induces those stress neurotransmitters, which will actually hamper your progress. Here is a clapping exercise that I like to do. Here's the quarter note. If you would clap along, that'd be great. 1, 2, ready, go. Great. So let's say I need you to learn this piece. I'm your director, and we're struggling with rhythm right now. So to help teach this piece in a quicker manner, I'm going to say, think of the words to Jingle Bells as you clap along. Dashing through the snow, and just clap to that rhythm. So here we go. Think of that. 1, 2, ready, go. Now, right here, some of you may have clapped a dotted eighth 16th rhythm instead of straight eighth notes. And what happened was that this far in the piece, you probably had zoned out and were just clapping along to the words and rhythms that you had grown up learning. So let's say we were going to change everywhere this rhythm in Jingle Bells. It would take a large amount of time and slow practice to eventually eliminate the dotted eighth 16th rhythm to having just the straight eighth notes. So you played it wrong because you had learned it over time, and that memory overrode what you were actually saying. You were relying on that instead of focusing what was on the page. Hence is why sometimes wrong notes in our etudes or solos are so hard to correct, because they're just ingrained in there. So the benefits of breaking down our practicing is that we're able to focus on the different aspects without the stress, such as the pitches, such as the rhythms. And eventually, when we become more comfortable with those aspects, we can combine them together. As I stated earlier, modeling is a great way to put these together, maybe before you're ready to actually play it. It gives the brain a chance to go through the correct pathways in a positive, helpful manner. The importance of mentors, and I think just emerging yourself around great artistry. It's been shown that the players we looked up to today, or the great players of the past, have probably grown up in an environment where they're surrounded by great artistry, and they're able to become immersed in that. Many institutions have a recital attendance credit that's mandatory for most freshmen, sophomores. And what happens is that these students go to these concerts and just basically punch their ticket. A conversation needs to happen of why these are important, why that going to these different types of concerts will actually add more tools to their toolbox. As brass players, we can learn a lot from going to orchestra concerts, vocal recitals, even piano recitals, and so And here is a list of books that I have found enjoyable to read on this topic. This is a topic that I myself will continue to read and research about and have enjoyed this journey so far. I hope you've enjoyed today's video. If you have any questions or comments or would like to discuss it, I can be reached at jlbz68@mail.umkc.edu. Thank you for watching today.